Mathematics in the ancient world could be defined a bit more easily than some of the other sciences. The primary focus of ancient mathematics was geometry, and the majority of what I'll speak about today is the various different developments and focuses of writers who talk about geometry. The ancients did distinguish between geometry and arithmetic, and I will talk a little bit about ancient Greek arithmetic as well. The other distinctions that we now make, such as between pure and applied maths, were more vague and porous in Greek times. I've already talked to some extent about applied geometry in the form of astronomy, and of course a lot of geometrical innovations were driven by these kinds of applications, particularly by astronomical problems and questions. And I will return to some of what we would think of as more applied topics next week, including some stuff on mechanics. But the authors I'll talk about today are more what we think of as pure mathematicians. They include Thales, Euclid, Archimedes, Apollonius, Diophantus and Pappus. One feature of Greek mathematics as identified by Reviel Netz, which I think is an interesting observation, is that unlike some of the other sciences of antiquity, where there are a comparatively large number of practitioners, say medicine, and you really got the appearance of kind of schools of thought, mathematics in the sense we'd think of it, sort of pure mathematics, seems to have been done by a really small number of people in the Greek world, and therefore things are often done in relatively esoteric ways, and it's quite hard to discover kind of schools. There's clusters of focus around certain topics and problems, but it makes it quite hard to think about an idea of a development of sort of competing theories that then one wins out or so on. There's obviously mathematicians influence each other. We don't know very much about the sort of contacts and communications mathematicians who lived at the same time as each other might have had. And clearly there is you see, some things proved early on that then get used later on and are taken as standard. So there is development in that sense. But it's quite different from our modern picture of how mathematics operates. More than any of the other sciences, I think we tend to see mathematics as one of those things where there's just kind of a clear picture of progress and development. There's obviously some exceptions to this in modern history. The crisis of the late 19th and early 20th century in mathematics is a really good example of a disruption to this idea of progress. But nevertheless, we understand mathematics very much as a sort of community of practitioners all building on each other's work. That sort of picture is much harder to trace in the ancient world just because of how few people are working. So I'm going to try in this lecture to give you a flavour of some of the topics that people worked on and to show you a couple of ancient mathematical proofs. If it feels like a bit of a sort of partial or patchy story, that's because it is. I'll begin as usual with some pre-Socratics, so let's start now with some pre-Socratic geometry. The most famous theorem from antiquity is, of course, Pythagoras' theorem, which we all learn in school and which I won't bore you with as you'll be familiar with it. Pythagoras' theorem is very much representative of the sorts of problems that pre-Socratic geometry was concerned with, in particular proofs concerning similar angles and similar shapes. There's plenty of evidence that these sorts of problems were being considered long before in Egypt and Mesopotamia, a point I'll return to in a minute. One of the other earliest mathematical writers, other than Pythagoras, and I'll include my usual caveat that we have very little evidence about Pythagoras. We do know that the Pythagoreans as a group were doing these sorts of geometrical problems. One of the other earliest writers we have any evidence of is Thales, and I've mentioned Thales in previous lectures. I talked about him right at the start, about him as a Milesian philosopher, as a substance monist who claimed that water was the primary substance. But Thales' other main claim to fame is in geometry, and particularly in a theorem that's become known as Thales' theorem, which you may also have learned in school. In fact, it's one of a number of theorems attributed to him, all of which focus around angles and circles. It's not at all clear whether these theorems were in fact formulated by Thales. I mean, at some level, what does it matter? Like Pythagoras, Thales often tends to get appended as a sort of mythological, like, father of geometry or father of this, that, and the other. In any case, it's clear that many of these theorems do date back a long way. I'm going to show you Thales' theorem so you can get a flavour of the type of thing the pre-Socratics were doing before I speak a little bit about why he may have been interested in these issues. So first, Thales' theorem. So what is the theorem? Well, it goes like this. If you take a diameter of a circle and call that AC, and then you take another point on the edge of the circle and call it B, join those points up to make a triangle, then the theorem is that the angle ABC is a right angle, and that's, I'll put that on your screen now, so I should hopefully be able to talk you through this quite visually. So as we'll see in a minute, this is a theorem that gets used a lot in proving other circle theorems. It's one of those really kind of foundational things that's extremely helpful. So how do we show this? So if you're feeling particularly mathematically inclined, I would invite you to pause the video now and have a play around and give it a go. People of different mathematical abilities will be listening to this. I did quite a lot of maths at school, but haven't done maths for years and years and years. And I found it, I didn't spend loads of time on this. I'm not saying you should, but it's quite instructive sometimes when you try and give these things a go and just see what you get. There's a few things to bear in mind if you do want to have a go at it. Obviously, you don't have to. First, remember that you can't use any trigonometry. So those of us who learn algebra and trigonometry at school, as we do in the modern age, our first instinct on seeing a triangle is often to go, oh, well, I can prove that using trigonometry. Well, you can't do that. We're living in a world in which algebra doesn't exist. So any proof that you do, or any kind of reasoning you do, has to be based solely on geometry. So that's just reasoning about the shapes that you can construct, the angles, and the lengths of lines. It also helps if you're trying to get into the Greek geometrical mindset to try and think of angles and lines not as absolute quantities, but as ratios of one another. So looking for lines which are the same length, angles which you can reason about their relations to one another. Almost all Greek geometrical proofs revolve around arguments that say things like, oh, well, angle CD is the same as angle EFG, and we know that angle EFG is such and such because of this, because it's part of shape B, so on. So it's all this kind of relational reasoning. So it hardly ever actually invokes numbers, just relations. So if you are feeling mathematically inclined and want to have a go at thinking about how you might try and prove that, please give it a go now. If you're not, then no need to pause, and I will go on and give the proof in just a second. The proof of Thales' theorem revolves around one key idea, and that is that you've got this triangle in a circle with angle ABC on the edge of the circle. You're trying to show that that's a right angle. So the key idea is that you subdivide angle ABC, and what you do is you drop a line in the middle of that angle to the centre of the circle, and you call that O. Now you've divided your triangle into two triangles. What you've gained some information. So your two triangles are now both isosceles. How do you know this? Well, you know this because in each of them, two of the sides are a radius of the circle. So the line B to O is necessarily a radius, but also because AC was originally a diameter of the circle, it means that CO and AO are also radii. So now that you've got this information, you can use the fact that an isosceles triangle, as well as having two equal length sides, has two equal angles. So what you do is what's illustrated here. You notice that angle OAB and angle OBA are the same, and I've labelled those alpha on the diagram. Similarly, angle OBC and angle OCB are also the same, and they're labelled beta on the diagram. From here, you use the fact that the angles in a triangle must add up to 180 degrees. That was known at that period. So you count up what you've got. You've got two alphas and you've got two betas. So 2 alphas plus 2 betas is 180. From there, you can reason that 1 alpha and 1 beta must add up to 90 degrees. And by the way, they wouldn't be thinking of this as 90 degrees. They'd be thinking of this as a right angle. They'd be thinking of this as the angles in a triangle add up to 2 right angles. 1 alpha and 1 beta, 2 alpha plus 2 beta add up to 2 right angles. So 1 alpha and 1 beta must add up to 1 right angle. Therefore, angle ABC, which is an alpha plus a beta, must be a right angle. And this works for wherever B is. You can slide it around the circumference of the circle. It doesn't matter what kind of shape the triangle is. It just has to be on the circumference of the circle. So sometimes, so that's just an example to give you a flavour of what kind of things are being done. Obviously, it gets a lot more complicated than that quite quickly, but that's the kind of proof, that's the kind of reasoning. And once you get your head into it, it is you know once you start thinking in those terms and you start thinking, oh well, I can't use trigonometry, I can't do it this way. You do get into that reasoning. Sometimes scholars have asked why Pythagoras' theorem and Thales' theorem were of interest to Greek thinkers. Why were they doing any of this stuff? And that's never an easy question to answer. I mean, what's the point of maths is quite a difficult question to answer. Maths is, in many people's view, one of those things that's both quite concrete and quite abstract at the same time. One argument I quite like, which is articulated by a scholar called Robert Hahn, who wrote a book called The Metaphysics of the Pythagorean Theorem, he talks about Thales' travels to Egypt and what was already known in Egyptian and Babylonian maths of the period. Hahn's theory then goes on to argue that Thales and Pythagoras both had a fundamentally metaphysical interest in right-angled triangles. Those of you who know the Molesworth books by Ron Searle might remember this diagram, which I really like, of Pythagoras hunting triangles. Quite a specific cultural reference. No worries if you haven't encountered this. But I think regardless of whether you've seen this specific incarnation, it's one of those things we think, Pythagoras, triangles. And Hahn says this is basically a correct instinct. They were actually metaphysically interested in triangles. His view is that this focus on triangles is the earlier stage of the project that Plato would later be engaged in, which I talked about in a previous week. So that's the explanation of the underlying mathematical structure of the world through his theory of the substructure of the elements in their constituent triangles. And you'll remember from a previous lecture I talked about that, how the 4 elements were all made up of these constituent triangles, and that was a kind of leap from understanding the physical world to understanding a kind of remember, it's not the same as the world of the forms in Plato, it's a kind of intermediate mathematical world, and I'll come back a bit at the end to that. So for Hahn, this is what Thales and Pythagoras were. They were an early stage of this, and this makes sense for people like Thales because they are substance monists. They have a fundamental view that the world is made up of one underlying thing. In this case, not water, as Thales is his physics is based around water, but here's a kind of underlying view that the world actually can be reduced to right-angled triangles. We do indeed have ancient reports that 2 of Thales' feats performed in Egypt were measuring the height of a pyramid using similar triangles and the distance of a ship which was away at sea and that he could see from the horizon. These were done using geometrical reasoning using similar triangles. So you've got a right-angled triangle of this size, you've got a right-angled triangle of this size. If you could compare the ratios of those triangles, you can then reason about the distances. Why were people so interested in those methods like similar shapes or constructing identical areas with different shape perimeters? One of the very common things that people are interested in Greek geometry is something like how do you construct a circle which has the same area as a right-angled triangle? Why would you be interested in that? Well, Hahn and others have suggested that there's a practical element to this. There's a kind of practical underlying motivation that this is really ultimately, in its first incarnations, about agronometry, that is, land measurement. So in particular in Egypt, where Thales is meant to have travelled, The Nile floodplain is really huge. The Nile floods in such a way every year that the boundaries of the fields on the floodplain after the floods are often quite different from what they were before. It would, for that reason, be extremely helpful to be able to do quite sophisticated calculations about similar shapes in similar areas to ensure that the field boundaries are still, you're still retaining the same amount of land that you're meant to. This is just a speculation. Hahn's work in other spheres also looks at these sorts of problems, particularly the relationship between pre-Socratic thought, which is usually taken to be quite abstract, and how it might relate to applied or concrete problems and technologies in the world of the time. One of his particular interests is in Anaximander, also a substance monist, and how he might have been influenced by architectural thinking about the kind of idea of architectural units and how you scale units to make a building, how the kind of substructure relates to the macrostructure. Hahn's views aren't uncontroversial, and a lot of what he says, obviously, is by its nature, has to be quite speculative. But what he's doing here, I think, is asking an interesting question, a question that's quite difficult to ask and quite difficult to answer, which is, why do maths? And that takes us quite neatly to our next figure, Euclid. So next I'm going to talk about Euclid. Very little is known about when and where Euclid lived. He's thought to have been around in around 300 BC, but we only have quite vague testimonies about him. You will have heard of Euclid's Elements, and you may be familiar with some of the contents. This is his sort of major mathematical work. It begins from some definitions of geometrical objects, and it proceeds to build up to more complex plane geometry and solid geometry. It covers a bunch of stuff, actually, including rectilinear figures, bisecting arcs, constructing circles, round figures, areas, that sort of thing. But it also has some arithmetical topics. It includes some stuff on prime numbers, commensurability, and so on. It's from Euclid that we get the notion of axiomatics. So what does that mean? What's an axiom? So axiom has slightly different meanings in maths and philosophy, and you can get very far into this rabbit hole. But a basic definition is that an axiom is the most kind of primary level postulate you can get to. So it's an axiomatic system involves a kind of fixed number of basic assumptions, things you just pin down and you say, these things are the building blocks and we're going to take them as true. And from there you build things, reasoning with them. So an example of an axiom in Euclid is all right angles are equal to one another, which might sound obvious and indeed might even sound like a definition, and the lines between what counts as a definition and an axiom are not totally clear, as you can imagine. One of the most famous axioms used by Euclid is what's known generally as the parallel postulate, which is this, and I'll put a diagram up. So if a straight line falling on two straight lines make the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which the angles are less than two right angles. So as you see from the diagram, he's not actually saying anything particularly difficult here. He's just saying if you've got these two lines that are inclining inwards, eventually they'll meet on that side. But the fact that he takes this as axiomatic and not something that can be proved is something that's been remarked on quite a lot in the history of maths. Many attempts have been made to actually show that this is something that's subject to proof. And in fact, the development of other forms of geometry, non-Euclidean geometry, particularly in the 19th century, although there were some bits done on it in the 18th, came from saying, okay, but what about if we throw away that axiom and we don't include that one in the system? But anyway, so axioms, that's about as complicated as an axiom gets in Euclid. And then the rest of the work is built on proving steps using the axioms or things you've already previously proved. So how does this work? Let me take you through one of Euclid's proofs, and I'll discuss after that a bit more about what proof actually is. So a good if you want to read more about this, a good place to start is Serafina Cuomo, who's a historian of ancient maths, and she has written a thing in the Princeton Companion to Maths, which may be available online. Euclid's proofs have a regular structure. They are made up of 6 parts. They don't all exactly follow this, but this is pretty consistent throughout. So the first part is called the protasis, and it states simply what is going to be proved. So, for example, let's take the example of proposition 1-6. The protasis of that is, if in a triangle 2 angles are equal to one another, the sides which subtend the equal angles will also be equal to one another. Subtend for these purposes just means, so when a line subtends an angle, the lines drawn from its end form that angle at the point where they meet. So here's just a little diagram, just so you get what's being claimed here. So that's the first part. The first part is where you just say, here's what I'm claiming, here's what I'm trying to prove. In general terms, it's always set out as a general thing. The second part is called the ekthesis, and that's the setting out, and that's where you set out a specific construction. You sort of explain what you would do if you were drawing a diagram. So in the case of 1-6, that goes like this. You say, let ABC be a triangle having the angle ABC equal to the angle ACB. So that's where you explain what you would do to draw a diagram. And in fact, I'll come back to the role of diagrams, but diagrams were used. The third part is what's called the diarismos, the definition of the goal. So this identifies, it takes the picture you've just drawn, it identifies from that picture what the protasis is being applied to. So in this example, Euclid's text goes on, and the next bit says, I say that the side AB is also equal to the side AC. So that's taking the protasis, the thing about the sides subtending the angles, and it's saying, in this particular diagram, this is what we're talking about. The fourth part of the proof is known as the kataskeuo, or the construction, and this is the bit where you make some further geometrical constructions in order to demonstrate the diarismos. So in the case of the thing I talked about before, Thales' theorem, that was the bit where we said, okay, let's drop another line through this angle that goes to the centre of the circle. You add an extra thing and you say, to make this step, I'm going to do this thing, do some reasoning, and then get there. So in proposition 1-6 in Euclid, this is how it goes. So it says, if AB is unequal to AC, one of them is greater than the other. Fine, that's sound. Let AB be greater, for example. And from AB, the greater, let DB be cut off equal to AC, the less. Let DC be joined. So he's added, it's there on your screen, but he's added some constructions as a sort of, here's a test case. Let's do these steps and see what happens. The fifth part, known as the apodoxis, is the proof, and that's the step-by-step explanation of why your kataskeuo, why your construction shows what you want it to show, and why it gets you to the diarismos. So in this case, it's as follows. Since DB is equal to AC and BC is common, the two sides DB and BC are equal to the two sides AC, CB respectively, and the angle DBC is equal to the angle ACB. Therefore, the base DC is equal to the base AB, and the triangle DBC will be equal to the triangle ACB, the less to the greater, which is absurd. We specifically constructed it. This is now me, not Euclid, obviously. We specifically constructed it so that one would be less and one would be greater, but we've shown that they're equal. That's definitionally absurd. Therefore, you can't accept the premise that you made that construction on. So AB can't be unequal to AC. Therefore, it must be equal to it. And you've shown what you wanted to show in this particular diagram, which is that AB is equal to AC. The final part is known as the sumperasma, or conclusion, and that's just a restatement of the protasis after it's been showed, usually with the word therefore to start. So in this case, it's Therefore, if in a triangle two angles be equal to one another, the sides which subtend the angles will also be equal to one another. And so that's the structure of the proof. So sometimes Euclid instead gives some instructions rather than starting with a geometrical property. So sometimes instead of starting with a claim, he says to construct this, and then he goes through the proof of how you do that. But it's the same kind. It's really the same kind of structure. Most of the proofs also have diagrams. The manuscript history of diagrams is complicated and an interesting thing in and of itself, and there's been quite a good deal of argument over how original the kinds of diagrams that we get in our medieval manuscripts are, whether they're actually good reproductions of what ancient diagrams might have looked like, or whether they're not. Obviously, to some extent, you can tell in these cases from the texts, because clearly they are doing this kind of thing where you draw something and you put letters on it. But diagrams have their own history. It is very clear that what Euclid's doing is using diagrams, and it's very clear that the diagrams are considered to be an integral part of the proof. So for those of us who aren't kind of incredible geometry whizzes, looking at the diagrams is often by far the most important part of understanding a proof. And at first, when you're looking at the diagram, the rigid kind of 6-part proof structure can seem a bit unintuitive. But I think that's the right way to think about it. The Greeks were also looking at the diagrams. Serafina Cuomo says proofs were never conceived of by the Greeks, even ideally, as purely logical constructs, but as specific kinds of arguments that one applied to a diagram. And I think you'll see from the structure, the way he goes from the general, he then says, okay, construct, draw a diagram of this, do the stuff that relates to this specific construction, and then you step back up to the general level. As you'll have noticed from the example I gave, one of the steps in that proof was to construct a contradiction, to show what would happen if the lines were unequal, to push that to its logical endpoint, and then you're forced to conclude that it would be absurd, so the lines must be equal. This type of proof by contradiction, is one of the favoured methods in Greek geometry, but it's not the only one, and we'll see in a bit when I get onto Archimedes that another type, proof by exhaustion, is also characteristic of Greek maths. In general, Euclid's method is known as the axiomatic deductive method, and that simply is a term that says you've got some axioms and you make step-by-step deductions using the axioms or things you've already shown to show the next thing. Sometimes in histories of maths, especially in popular histories, you get this very idealised version of this. You read about it and it presents it as this sort of totally clean and perfect way of doing maths, where everything's spelled out and everything follows logically on. As you'll have seen from the proofs above, both the Thales one and the Archimedes one, that is the case. Everything is spelt out and it does logically follow on. But I always think of these a bit more like when you write out a neat version of a solution to a maths problem in your homework. It's not like you have included all the scruffy working out, any of the intermediate calculations, any of the kind of wrong avenues you tried, or indeed any of the heuristic methods you might have tried. So heuristic there being a term that means the method by which you search for or kind of land on the right approach. And I'll come back to that in a minute when I talk about Archimedes. One question that isn't asked that often about Euclid, but is quite a pertinent question, is why would you actually want to try and axiomatise geometry? After all, many of the more straightforward geometrical proofs that Euclid gives had been known or implicitly accepted for hundreds of years by the time he wrote. Many of the things that are in Thales, come up again in Euclid. What's different about what Euclid is doing, and why is he doing that rather than just working on kind of new stuff? So some scholars have argued that Euclid's methods may have been quite influenced both by previous mathematicians, but also by some of the philosophical questions that were being worked on about certainty and change. And one of the figures I talked about in a previous lecture at some length was Zeno, and Zeno's philosophical paradoxes that were nevertheless very applicable to mathematical structure. So he talked a lot about, Zeno's paradoxes get really a lot at the question of what does it mean for something to be continuous or for something to be discrete. And I think you can see in Euclid's definitions an awareness of those sorts of philosophical questions when he tries to define things like points and lines, because in fact those things were being challenged by the skeptics. As I mentioned, Euclid's usually dated to around 300 BC, and although we really do know very little about him or his life, it's safe to say that at that period the impact of Zeno and the skeptics would still be being felt. But next I'm going to talk about a couple of mathematicians who do go, not to say that Euclid doesn't go beyond what's done before. I mean, we simply don't have the evidence to really know that, but it's safe to say that plenty of the stuff in the Elements is innovative. Nevertheless, I'll talk about two mathematicians who really do start kind of going off quite a long way into geometry and pushing the boundaries, and they are Archimedes and Apollonius. I'll talk quite a lot about Archimedes next week in the context of mechanics and engineering, which is what he's probably most famous for, apart from obviously that story about him saying Eureka, or indeed Heureka, I've found it, when he sat in the bath. Unlike other mathematicians, we know quite a lot about Archimedes. We have several biographical accounts from later writers, including Plutarch and then the much later Byzantine chronicler John Tzetzes. For this reason, Archimedes' life is pretty well attested. He lived in Syracuse in Sicily, and he was probably in his 70s during the Roman invasion of Sicily in 212 BC during the Second Punic War. Archimedes was killed in this invasion. There's a story that he refused to stop drawing geometrical diagrams in the dust while some Roman soldiers were speaking to him, and so they killed him. Alongside his mechanics, he did quite a lot of geometrical work on conic sections in particular. His most famous proof is found in the text known as the sphere and cylinder, and it demonstrates that the volume of every sphere is 2/3 that of the cylinder circumscribing it. I'm not going to show you that proof because it's really hard. Archimedes sometimes follows an axiomatic deductive method like in Euclid. He's better known, though, for what's called the method of exhaustion, which isn't his invention and probably predates him by a long while. We have some examples in what we know of Eudoxus, the same guy I talked about quite extensively in the astronomy lecture. But Archimedes is associated particularly with the method of exhaustion because he does it quite a lot. For example, his approach to the problem of how to calculate the area of a circle by comparing it to the area of a given right-angled triangle. I mentioned that earlier. So for Archimedes, the way he approaches this is to show first that the area of the circle can't be larger, and then that it can't be smaller, so that they must be equal to this triangle he's constructed. But his method of doing this is sort of quite iterative and implicit. It's not the Euclidean style where you or even the style you find in Thales where you just kind of really clearly geometrically show everything. It's much more of a, well, it can't be this, it can't be that, it can't, okay, fine, we've narrowed it down. Apollonius of Perga, who lived slightly later, died in about 190 BC, was another geometer and astronomer, and his main surviving text is called the Conics. We know that it had 8 books, only 7 have made it down to us, and the last of these only exists in Arabic. Apollonius wrote about astronomy and arithmetic, but those works aren't extant. So like Archimedes, he was very interested in cones and curvilinear forms. The conics, like Euclid's Elements, begins from a set of definitions. This time they're not of all geometrical figures, but of cones and conic sections. And then the theorems that he goes on to prove include things about the various shapes derived from conic sections, including the parabola, the hyperbola, and the ellipse, which are illustrated on your screen now. And then other theorems are about tangents, asymptotes, that kind of thing. Some of them are to do with the construction of conic sections, equal or similar to a given conic section, which is also, you can see, could have practical uses, although perhaps this time is really much more kind of hypothetical and mathematical. Like Euclid, Apollonius usually gives axiomatic deductive proofs, which give a general statement diagrams and logical steps. Apollonius's work wasn't fully recovered in the West until quite late on in the Renaissance, and it's some of the most geometrically difficult work we have existing from antiquity. A lot of it really wasn't kind of worked through again. It was worked through in the medieval Islamic world, but in the West it really wasn't kind of worked through and understood until really quite late on in the Renaissance. I'm not going to try and take you through any of the proofs. One of the things that is interesting about Apollonius and indeed Archimedes is that because their work often is to do with approximating the area circumscribed by a conic section, and you'll have seen from that diagram of the parabola, if you've done any calculus in school, or indeed later, you will know that one of the main aims of calculus, kind of initially, is in calculating the area circumscribed by a conic section like a hyperbola or a parabola. And one of the things that is a quite interesting side story in the history of maths, which I'm not going to get into, is the way in which their geometrical approaches that don't invoke the notion of infinity in the way that the calculus does. Those get read later on around the time of the development of the calculus as, maybe they were actually doing something, secretly with infinity. Infinity is actually not really a thing at all in Greek mathematical calculations. So the way that they're constructing these kind of really abstruse geometrical proofs is seen through it's quite hard to see it through the original geometrical lens if you're a modern person who is quite familiar with calculus, because your approach would be like, why don't you just why don't you just do that by calculus? Like, it's very easy, whereas doing it geometrically is very hard. And so it's quite difficult reading those works, if you do even understand the proofs, which many of them I don't, to get into that geometrical mindset. On a related point, I want to come back to Archimedes and something I mentioned when talking about Euclid, and that's the idea of the heuristic. Everyone knows once you've got this kind of perfect axiomatic deductive proof, clearly you've done some previous working out. It's not like you are writing it as you go along. But the question of what it means to kind of work out what the next step is. So even more so than proving things by contradiction or other methods like that, the method of exhaustion does often leave you wondering, well, how did Archimedes get there in the first place? How did he find the right place to start exhausting this? So, for example, quite frustratingly, sometimes Archimedes makes statements like, okay, well, this sphere is 4/3 the area of this cone. And then he goes through and proves it geometrically. And he uses that protasis, that claim, it's 4/3 the size, and he might construct a contradiction there, or he might do something else, but he's using that statement, well, it's 4/3 the area, and you think, well, hang on a minute, how did he even get to this figure? How did he arrive at the hypothesis that it's 4/3 in the first place? You might want to say, this isn't a very interesting question. It's the case in all science that people arrive at their hypotheses by some complicated mixture of factors. Sometimes they're educated guesses, or they're some form of analogical reasoning from other similar problems that they've seen. And with Archimedes, it's true that these big historical debates about his heuristic really occurred around the same time as the development of the calculus, as I just mentioned, or in fact, this was just before. Which is at a time when the notion of what counted as a mathematical demonstration was changing quite a lot. Previous to this period, the kind of late 16th into the 17th century, previous to that, you always have this very rigorous Greek-style geometrical axiomatic deductive proof. But you begin to get these other notions at this period among mathematicians of what's acceptable within a mathematical proof. Scholars like the Oxford mathematician John Wallis, one of the early scholars of the history of maths in the late 17th, I think. That might be wrong. I'll put a correction on the screen if I need to. Anyway, he argued that Archimedes was using the method of exhaustion for some of his mathematical, particularly his arithmetical results, and and that, there wasn't this heuristic. But a treatise called On the Mechanical Method was discovered in the Archimedes palimpsest in 1906. So this is long after John Wallis wrote. The Archimedes palimpsest was a very strange manuscript discovery where a lost bit of Archimedes was recovered after this manuscript had been kind of in a library and then in a private collection, and then it had moved here and here and here, and no one had seen it. So it was this kind of, it kind of reappeared in 1906 and then disappeared again, and then reappeared in, I think, the 90s. Anyway, this lost treatise, here's what Archimedes has to say on the matter. So I quote, "I've thought it fit to write out for you and explain in detail the peculiarity of a certain method with which, furnished, you will be able to make a beginning in the investigation by mechanics of some of the problems in mathematics. I am persuaded that this method is no less useful even for the proof of theorems themselves. For some things first became clear to me by mechanics, though they had later to be proved geometrically, owing to the fact that investigation by this method does not amount to actual proof. But it is, of course, easier to provide the proof when some knowledge of the things sought has been acquired by this method, rather than to seek it with no prior knowledge at the outset. Therefore, I'll write out the very first theorem that became clear to me through mechanics, that any segment of a section of a right-angle cone is 4/3 of the triangle having the same base and height. 4/4 of the triangle having the same base and height." End quote. So what are we to make of how Archimedes might have mechanically shown this result, or this result about the area of the cone of the triangle? If you look on your handout, I've redrawn a diagram from Ivor Bulmer Thomas's Loeb translation of Archimedes, where he does the geometric proof. How would you do that mechanically? I'm going to guess that this isn't one of those Wallis cases where he's talking about doing exhaustion by polygons, which is one, where he circumscribes something with polygons and he just exhausts it. I think here there actually is some mechanical thing going on, as Archimedes says. And if I was Archimedes, I think I would probably do it by having wooden cutouts of these shapes and perhaps weighing them or submerging them in water. Maybe the bath story does have some truth in it. And seeing in the disparity in the water they displace. Doing something like that will give you an accurate enough sense that this one's 4/3 of this one, and you can then go and try and prove it geometrically, which is what Archimedes does. So, maybe these people who thought, Archimedes does have this lost heuristic, maybe there was something in it. I'll come back to Archimedes' more clearly mechanical innovations next week. But for now, I'm going to turn to a few figures in later antiquity and come back to the question I raised in week 2 when I was talking about epistemology, and just say a few things about the epistemic status of mathematical objects. What did ancient thinkers thought it meant to have mathematical knowledge? I'm going to talk briefly about a few later mathematicians, some of whom worked on similar topics to their predecessors, and some of whom were quite different. One who was quite different was Diophantus, who lived in Alexandria in the 3rd century as far as we know, and he's best known for his Arithmetica, a work of number theory and arithmetic. Diophantus' work is unusual in that it's pretty separated from geometry. There's hardly anything geometrical in it. It's sometimes taken to be algebraic, and of course the boundaries between the sorts of problems studied in arithmetic and algebra is a bit porous, but it's really important to note that algebraic notation as we know it, the equals sign, the notion of zero, and so on, are all later inventions. Those don't come up until medieval Islamic mathematics. So although some of the problems that Diophantus is doing are things that convert extremely easily into algebra, and he is talking about quantities and the equality of quantities and so on, it's not quite algebra as we know it. So, his interest in saying, this quantity is equal to this quantity is rather different, admittedly, from the way in which most of Greek mathematics thinks of equality as a geometric relationship of identity. As we saw with Thales, that's all about kind of similar triangles, and this shape is the same as this shape. And that is a bit different from quantity. Obviously, the Greeks had a notion of things being equal to each other, but the idea that you do kind of long patterns of manipulation of quantities is not really their way of approaching these problems. So one of the things that Diophantus shows, for example, is that numbers, well, this is now written in algebraic notation, but numbers of the form 4n plus 3 can't be the sum of two squares. And that's one of those neat little number theory results that that we don't really think of as a very kind of Greek style of doing mathematics. It's been speculated that he also knew that every number can be written as the sum of four squares. It's not sure if he proved that. Probably not, because that wasn't proved until the 18th century by Lagrange. But he's clearly very interested in these sort of properties of numbers. A mathematician who did much more conventional Greek geometric work was Pappus, also of Alexandria, who lived, we think, in about the late 4th century. He used to be thought of primarily as a compiler of previous works, and he does provide these very useful summaries of previous people's work, including Euclid. But actually he did a lot more spherical and curvilinear geometry of his own. His most famous theory is one about hexagons, which I probably don't have time to go into, but which is quite an interesting piece of geometry. Another interesting figure from the later period is Proclus, who was around in the 5th century AD, and he wrote a commentary on Euclid's Elements. I bring him up because he was also known as a philosopher. He was a late Platonist, and he made quite a few innovations in Platonic philosophy, particularly in epistemology. So one of the interesting things he has to say is about the status of mathematical objects. You may remember from lecture 2 on epistemology that one of the levels of knowing in Platonic theory, so Plato had these 4 levels of some of them constituted knowledge and some of them were more like belief or understanding. And there was the divided line. There were the 2 kind of more secure types of knowledge above the divided line and the more speculative things underneath the divided line. Well, Dianoia was the first one above the divided line, so level down from episteme, which is the absolute knowledge of the forms, but Dianoia was this kind of intermediate level knowledge. And it's not super worked out in Plato, although it's been argued that he thinks it to apply to mathematical objects. Well, Proclus takes this a lot further. Proclus argues that mathematical objects were exactly of this kind, and that they were they provided a kind of bridge between the noumenal world of the forms and the nonetheless quite sort of mental and abstract world of mathematics. They were the mental and abstract world of mathematics. They provided a bridge between the noumenal world of the forms and the sensible world of objects, about which you could only have things that didn't constitute proper knowledge. So I quote from Proclus here. Mathematical being necessarily belongs neither among the first nor among the last and simple kinds of being, but occupies the middle ground between the partless realities, that's the forms, which are simple, incomposite and indivisible, and divisible things characterised by every variety of composition and differentiation. The unchangeable, stable and incontrovertible character of the propositions about it, so that's mathematical propositions like we find in Euclid, shows that it's superior to the kinds of things that move about in matter. But the discursiveness of mathematical procedure, its dealing with its subjects as extended and its setting up of different prior principles for different objects, these give to mathematical being a rank below that indivisible nature that's completely grounded in itself. So I think what he's saying here is mathematical being clearly has some kind of more stable form. It's somehow more concrete than things we can know about the sensible world. Nonetheless, the very fact that we have to use axioms, the very fact that we start from slightly different starting points when we're dealing with, arithmetical objects as opposed to geometrical objects, he thinks that's kind of evidence that these are not as perfect as the knowledge of the forms would be, and that for knowledge of the forms, you don't have to have messy things like axioms or you don't have to kind of set things out in extended logical proofs. It's more immediate. So I think this is quite an interesting theory, and I think this is in some ways how many mathematicians actually still think about mathematics. So this week I've talked about maths. I've shown you a few Greek geometrical proofs, including one from Thales and one from Euclid, but I've also talked about some of the other things that came up in Greek maths, such as the arithmetic interests of Diophantus and others. Next week, I will talk a bit more about some of what we might like to think of as the applications of maths. Particularly, I'll be talking about engineering and technology, although if I have time, I may talk a little about harmonics and optics.